December 21, 1944. The frozen earth near Malmedy, Belgium. Obergefreiter Hans Richter crouched in his foxhole, 4 feet deep with overhead logs, exactly as training prescribed. He had survived Stalingrad, fought through the Kursk salient, endured 3 years of Soviet artillery that had taught him to read the sound of incoming shells, to calculate where they would land, to know when his foxhole would protect him and when he needed to run. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The American barrage that morning shattered every assumption he had built about survival. The shells were detonating in mid-air, 20 to 30 feet above the snow-covered ground before they reached the earth, not occasionally, as timed fuses sometimes did when set correctly. Every single shell, with mechanical precision. At the exact same height, Richter pressed himself against the frozen dirt as hot steel fragments whistled downward into his foxhole, the one place that should have been safe, watching the man beside him convulse as shrapnel tore through his shoulders and skull from above. In 3 years of war, Richter had never felt helpless, until that moment. 4 hours earlier, examining an unexploded American shell in the pre-dawn darkness, Richter's battery commander, Hauptmann Friedrich Weber, had discovered something that contradicted everything German artillery doctrine taught about what was possible. The shell's nose contained what appeared to be a complete miniature radio station, smaller than a wine bottle, packed with glass vacuum tubes that had somehow survived being fired from a gun at accelerations that should have pulverized them into dust. German ordnance engineers had concluded a decade earlier that such a device was theoretically impossible. The Americans had not only built it, they were manufacturing them by the tens of thousands, firing them as casually as conventional ammunition. This single realization would fundamentally alter German understanding of the industrial war they were losing. The contrast was stark and humiliating. While American artillerymen simply loaded shells and fired, knowing each round would detonate at the optimal height automatically, German gun crews were still performing calculations that hadn't changed since 1918. Every timed fuse required manual setting before firing. An artilleryman would estimate the range to target, calculate the shell's flight time, then physically rotate a graduated ring on the fuse to the correct number of seconds. The process took 15 to 30 seconds per shell. It required mathematical precision under combat stress. It assumed the target wouldn't move. It depended on accurate range estimation, which required clear visibility and trained observers. When weather was poor, when targets were moving, when infantry needed immediate fire support, German timed fuses became nearly useless. The margin for error was measured in human lives, on both sides. Set the fuse a half-second too long, and the shell exploded beyond the target, too short, and it burst harmlessly in the air or killed your own troops. German artillery tables from 1944 listed 43 variables that could affect shell flight time, from air temperature to propellant age to barrel wear. Artillerymen consulted printed charts, made corrections for wind and elevation, then manually set each fuse hoping their calculations were correct. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. They would learn if they had succeeded only when the shells exploded, usually too late to adjust fire before the target moved or returned fire destroyed the gun position. The Americans, by December 1944, had eliminated this entire process. Their proximity fuses required no calculation, no setting, no adjustment. The shell itself measured its distance from the target and detonated automatically at the optimal height for maximum lethality. The story of how this technological chasm opened between German and American artillery began not on the battlefield, but in the industrial and scientific infrastructure of two nations pursuing radically different approaches to weapons development. Germany's artillery fuse technology in 1944 remained fundamentally unchanged from the Great War. The Zeitzünder, or time fuse, used a powder train that burned at a predictable rate. When the shell fired, the acceleration ignited the powder. After burning for the preset time, the flame reached the detonator and exploded the shell. The system was reliable, inexpensive, and completely dependent on human calculation. German engineers understood the limitations. They had explored proximity fuses as early as 1930, developing over 30 different prototype designs, acoustic sensors that would trigger on aircraft engine noise, electrostatic detectors that would respond to the charged surfaces of metal aircraft, photoelectric cells that would detect changes in light. Radio-based systems similar to what the Americans eventually built. Every approach faced insurmountable obstacles with available technology. Acoustic fuses couldn't distinguish between friendly and enemy aircraft. Electrostatic sensors had limited range and were unreliable in humid conditions. Photoelectric cells required clear weather. Radio-based proximity detection required vacuum tubes small enough to fit in a shell nose, yet tough enough to survive artillery acceleration, which generated forces 20,000 times stronger than Earth's gravity. By 1939, German researchers concluded that proximity fuses could not be developed with existing technology. When Hitler issued his directive in 1940 prioritizing only weapons that could reach production within 6 months to support the coming invasion of the Soviet Union, Germany's proximity fuse programs were among the projects terminated. Limited research resumed in 1944 at Rheinmetall-Borsig, far too late to affect the outcome. The decision was logical given German industrial capacity and strategic priorities. Proximity fuses would require massive investment in electronics miniaturization, new manufacturing processes, quality control systems that didn't exist in German industry, and coordination across multiple industrial sectors. Germany in 1940 lacked the industrial margin for such ambitious development. Every resource was committed to immediate production of tanks, aircraft, submarines, and basic ammunition. The Americans took the opposite approach. In June 1940, 2 months before Germany abandoned proximity fuse development, the United States National Defense Research Committee formed under Vannevar Bush and made the proximity fuse their second highest priority after radar. The decision was remarkable. America wasn't yet at war. The weapon would cost over $1 billion 1940s dollars. Success was uncertain. The technical challenges appeared insurmountable. The Americans committed anyway because they could afford to fail, and they understood that industrial capacity creates military options. Section T at the Applied Physics Laboratory of Johns Hopkins University, established in a rented Chevrolet garage in Silver Spring, Maryland in March 1942, brought together over 1,000 scientists and engineers led by physicist Merle Tuve. Their task was to make the impossible routine. The technical challenge was elegant in concept, brutal in execution. Create a miniature radio transmitter and receiver that could fit in a shell nose, survive acceleration forces that would liquefy human tissue, function in extreme temperatures, spin at 25,000 revolutions per minute, and operate perfectly for the few seconds between firing and target impact. Then manufacture it by the millions. The radio circuit would emit waves at 180 to 220 MHz. When these waves reflected off the ground or a target, they would return at a slightly different frequency due to the Doppler effect. When the frequency shift indicated the shell was 20 to 30 feet from the ground, an electrical circuit would close and detonate the explosive. The theory was sound. Making it work required solving problems that the world's leading engineers had declared impossible. Consider the vacuum tubes. Conventional tubes designed for radios or hearing aids would shatter instantly under artillery acceleration. James Van Allen, a young physicist who joined the laboratory in April 1942, led the development of what the team called ruggedized tubes. Working with Sylvania and Raytheon engineers, Van Allen redesigned tubes from first principles. The glass envelopes were thickened and carefully heat-treated to prevent fracturing. The internal filaments and grids were shortened and reinforced with heavier cross-sections. The tubes were potted in wax inside the fuse body to cushion shock. Every design iteration was tested by firing complete fuses from guns at the Dahlgren Naval Proving Grounds in Virginia into soft earth that would catch the shells gently enough to recover them. Engineers examined the tubes under microscopes to see what had broken, redesigned the weak points, and fired again. Through hundreds of test firings and thousands of design modifications, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized production tooling. The engineers were confident they could improve reliability during manufacturing scale-up. By early 1943, reliability exceeded 90%. But vacuum tubes were only the beginning. The Fuse needed a power source. Conventional batteries were too large and deteriorated during storage, particularly in tropical heat. Engineers developed a reserve battery using liquid electrolyte, kept separate from the battery plates until activation. When the shell fired, centrifugal force spun the electrolyte into contact with the plates, generating electricity instantly. This gave the batteries indefinite storage life in any climate. The Fuse required multiple safety mechanisms. It couldn't arm until well clear of the gun barrel to prevent premature detonation that would destroy the gun and crew. It needed protection against radio interference from the ship's own radar or nearby transmitters. It required frequency filtering to prevent detonation when fired at low angles over water, where reflections from the surface could trigger premature explosion. Each safety feature added complexity and components. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components, more sophisticated electronics than existed in most German radar installations. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most advanced piece of miniaturized electronics that existed in 1942. The contrast with German fuse technology was absolute. A German sights-under 23-time fuse, standard equipment in December 1944, contained exactly 7 components: a brass body, a powder train, a detonator, a safety pin, a graduated setting ring, a spring, and a firing pin. Total manufacturing time per fuse was approximately 4 minutes using semi-skilled labor. Cost was less than 1 Reichsmark. Reliability was over 95%, assuming correct manual setting. The German fuse was a masterpiece of mechanical simplicity, refined over decades to be robust, cheap, and effective within its limitations. Those limitations were becoming catastrophic. German artillerymen in December 1944 faced tactical situations where their time-fused shells were nearly worthless. In the Ardennes forest, where Hitler launched his final offensive, German forces needed artillery support against dispersed American infantry in heavily wooded terrain. Time-fused shells required precise range calculation, but visibility was limited and targets were moving. German forward observers couldn't accurately estimate ranges through dense forest. Gun crews set fuses based on map coordinates and guesswork. Most shells either exploded too high to be effective or impacted the ground, sending fragments harmlessly into trees and earth rather than into American positions. American artillery, using proximity fuses, simply fired. The shells automatically detected the ground or treetops and detonated at optimal height every time, regardless of visibility, regardless of range estimation accuracy, regardless of whether the target had moved. The psychological impact on German troops was immediate and devastating. Soldiers who had survived years of combat, who had learned to gauge danger and take appropriate cover, suddenly found their survival instincts worthless. American artillery was striking with impossible precision through fog and forest, killing men in positions that should have been safe. German after-action reports from January 1945 captured the confusion. One Panzer Grenadier officer wrote that American artillery appeared to have perfect observation of all positions despite weather that prevented visual reconnaissance. Shells exploded at optimal height over concentrations of troops with consistency that seemed impossible. The officer concluded, incorrectly, that Americans must have deployed some new type of aerial observation system. He never suspected the shells themselves were making the decisions. Another report from the 346th Volksgrenadier Division noted that American artillery fire, even when poorly adjusted for range, achieved devastating effectiveness through consistent airbursts. The report's author, trained in traditional artillery doctrine, couldn't understand how shells that appeared to be missing their targets were still causing massive casualties. He recommended dispersing troops more widely and avoiding any identifiable terrain features. The recommendations were tactically sound but strategically futile. Proximity fuses didn't care about dispersal or concealment. They detected the ground itself and detonated. The manual process German artillery crews endured highlighted the gap. Before each fire mission, German gun commanders consulted firing tables listing corrections for dozens of variables. Air temperature affected powder burn rate and therefore muzzle velocity and flight time. Cold weather in December 1944 meant shells flew slower and shorter than summer trajectories. Propellant degradation from age or moisture required correction. Barrel wear from thousands of previous firings changed muzzle velocity. Elevation differences between gun position and target altered trajectory. Wind speed and direction deflected shells. Even the rotation of the Earth, the Coriolis effect, mattered at longer ranges. After calculating all corrections, the gun commander ordered a specific fuse setting. An artilleryman physically rotated the graduated ring on each fuse to the calculated number of seconds, then loaded the shell. If calculations were wrong, if conditions changed, if the target moved, the entire process had to repeat. By the time corrected shells arrived, the target was often gone. American gun crews loaded proximity-fused shells directly from ammunition bunkers. No calculation, no setting, no adjustment. The shells handled everything automatically. The rate of fire advantage was substantial. A German battery firing time-fused shells could sustain approximately 4 rounds per gun per minute, with most of that time spent setting fuses. An American battery using proximity fuses could fire 8 rounds per gun per minute, limited only by loading speed. This doubled firepower translated directly to tactical dominance. When German positions needed suppression, American artillery could deliver twice as many shells in half the time, with every shell optimally effective. German return fire, delayed by fuse setting and hampered by poor visibility, arrived late with inconsistent results. The industrial statistics behind this tactical superiority were staggering. By December 1944, American factories were producing 70,000 proximity fuses daily. 5 companies conducted final assembly: Crosley Corporation, Sylvania Electric Products, Radio Corporation of America, Eastman Kodak, and McQuay Norris. Sylvania's Ipswich, Massachusetts plant alone manufactured 5,683,332 fuses, while also producing 95% of all miniature vacuum tubes used across the entire program, over 100 million tubes total. The Crosley Corporation in Cincinnati employed 10,000 workers operating continuously, achieving peak daily output of 16,500 fuses. The facility consumed more electricity than many small cities, maintained air conditioning to keep temperature within 2 degrees Fahrenheit to prevent thermal expansion affecting precision tolerances, and rejected 28% of completed units that failed quality standards. This rejection rate, which would have been catastrophic for German production, was acceptable to American planners because production volume was so massive they could afford to destroy more precision components daily than Germany produced monthly. More than 100 factories participated in some phase of production. Over 2,000 suppliers, ranging from copper mines in Montana to chemical plants synthesizing new plastics, provided materials. The workforce was predominantly female. At Sylvania's Ipswich plant, 9,000 of 10,000 workers were women, many recruited from local communities with no technical background. They worked in clean rooms with filtered air, using microscopes to verify component placement within tolerances of 20,000ths of an inch. Each worker typically performed one specific task, repeated thousands of times per shift, assembling electronics more sophisticated than anything in German military inventories. Security surrounding the proximity fuse was second only to the Manhattan Project. Workers signed secrecy oaths and underwent searches entering and leaving facilities. They didn't know what they were building. The device carried the deliberately misleading designation VT fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Even its use in combat was initially restricted to situations where duds couldn't fall into enemy hands. The first combat employment came on January 5, 1943, off Guadalcanal, when the cruiser USS Helena fired 3 salvos of proximity-fused shells at departing Japanese dive bombers, downing 1 aircraft with 3 shells. What would have required dozens of manually fused rounds was accomplished with 3 automatically detonating shells. Combat effectiveness exceeded every prediction. By mid-1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. Ships using proximity fuses required an average of 310 rounds per aircraft kill, compared to 1,162 rounds with conventional ammunition. The mathematics of air defense had been revolutionized. But through 1943 and most of 1944, the Pentagon absolutely forbade use of proximity fuses over land. The risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. Intelligence analysts estimated that if Germany equipped its anti-aircraft guns with proximity fuses, Allied bomber losses could increase by 300%. The strategic air campaign might become unsustainable, so the fuses were used only over water, where duds would sink beyond enemy reach. This restriction began cracking in June 1944, when Germany unleashed Von flying bombs against London. The small, fast, pilotless missiles were extraordinarily difficult to intercept. British defences initially destroyed only 17% of V-1s entering the coastal gunbelt. Prime Minister Winston Churchill authorised use of proximity fuses in anti-aircraft guns defending Britain. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming V-1s were shot down. The Von campaign demonstrated that proximity fuses were potentially war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land. The risk that seemed unacceptable in 1943 now had to be weighed against military necessity. On December 16, 1944, that calculation changed completely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 0531 hours, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's desperate final offensive in the west. The Germans struck through the Ardennes forest, aiming to split Allied armies and capture the vital Belgian port of Antwerp. Within days, German forces drove a Bulge 50 miles deep into Allied lines. Heavy snow and thick clouds grounded Allied air power. German commanders felt relatively safe from artillery because poor visibility made accurate observation nearly impossible. They were catastrophically wrong. Colonel Oskar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision that same morning. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received new ammunition, proximity-fused shells codenamed POSIT, but Supreme Commander Dwight Eisenhower had not yet authorized their use over land. Secrecy restrictions were still technically in place. Axelson decided the emergency trumped restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. For the first time in the European theatre, American artillery was firing air bursts with perfect consistency regardless of visibility or terrain. Each shell exploded 20 to 50 feet above ground, precisely calibrated for maximum effect against personnel. Fragments spread in a cone-shaped pattern, covering an area far larger than ground bursts. Foxholes provided no protection. Shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. They couldn't hear the shells approaching due to high velocity. The first warning was the explosion overhead. 3 days later, on December 19th, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. While German artillery crews still manually set fuses, calculating flight times and praying their estimates were correct, American guns simply fired, letting the shells make their own decisions. The tactical implications extended beyond raw effectiveness. German artillery doctrine required forward observers with clear lines of sight to adjust fire. In the Ardennes forest and winter weather, observation was nearly impossible. American proximity fuses eliminated the need for observation adjustments. Initial ranging shots were unnecessary. Shells didn't need to impact near the target to be effective. Air bursts at optimal height damaged everything within a 60-yard radius, whether the range calculation was perfect or not. This meant American artillery could fire effectively in conditions that rendered German artillery nearly useless. Lieutenant General George Patton, initially skeptical of new technology, became a convert after witnessing proximity fuse effectiveness. Near the Sauer River, his Third Army caught a German battalion attempting to cross with concentrated proximity-fused fire. By actual count, 702 enemy soldiers were killed. Patton wrote to the War Department describing the new shell with the funny fuse as devastating. He predicted that when all armies possessed this weapon, they would need to devise entirely new methods of warfare. The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Panzer Brigade 150, part of the elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery battalions fired proximity-fused shells with such devastating effect that the air bursts unnerved attackers so completely that some charged directly into American positions, seeking any shelter from overhead. Explosions. The attack was repelled by afternoon. German prisoners of war interviewed by American intelligence officers revealed the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable at loss rates of 15 to 20% per mission. But he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match, while their own artillery still used manually set fuses that required calculations their forward observers couldn't make in forest and fog. The Battle of the Bulge demonstrated how American doctrine had evolved to maximize fuse effectiveness. Forward observers called down fire not just on visible targets, but on suspected positions. Artillery batteries laid down barrage patterns covering entire areas. The proximity fuses meant every shell was an effective airburst. German tactical doctrine developed over years of warfare had to be completely rewritten. Traditional, defensive positions were suddenly death traps. Moving in the open during artillery fire remained suicide. Germans tried adapting by dispersing more widely and staying constantly mobile, but adaptation had limits. The proximity fuse fundamentally altered the equation. German units began exhibiting what American intelligence termed artillery shock syndrome, a condition specifically triggered by helplessness facing proximity-fused fire. Some units experienced discipline problems with soldiers refusing orders to move into areas under American artillery coverage. American intelligence reports noted German commanders offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. By January 1945, Wright Field in Ohio had developed electronic countermeasure systems designed to jam the fuse's radio signals based on the assumption that captured fuses would lead to German jamming efforts. But German engineers, having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, never fully grasped that miniature radio transmitters were inside every shell. They literally held the intelligence coup of the war without recognizing it. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. Ground combat intensified as well. During Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity, fuses set to detonate at rooftop level, showered entire city blocks with shrapnel, making defensive positions untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe might have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defenses equipped with proximity fuses might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. Meanwhile, German artillery crews were still manually setting time fuses on each shell, a process that hadn't fundamentally changed since 1918. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research and the reasons for its failure. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch that would trigger when detecting specific engine frequencies. Rheinmetall-Borsig developed an electrostatic fuse using capacitive detection to sense the charged metal surfaces of approaching aircraft. There were optical fuses using photoelectric cells, magnetic fuses detecting metal mass, and experimental radio fuses conceptually similar to the American design. But none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired with promising results. By then, it was far too late. Germany lacked the industrial capacity to establish mass production. Even if production facilities could have been built, the resources required would have competed directly with production of tanks, aircraft, and basic ammunition. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse program alone consumed over $1 billion 1940s dollars, equivalent to approximately $15 billion in modern currency. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. The production statistics were staggering beyond German comprehension. At peak output, American factories were producing 70,000 fuses per day. That represented nearly 3 million individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world daily. The cost per fuse fell dramatically as production expanded. In 1942, Each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased worker efficiency, and economies of scale that German industry simply could not match. At $18 per fuse, the weapon was expensive compared to conventional fuses costing pennies, but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness by up to 10 times was an obvious value proposition. By contrast, German time fuses cost less than 1 Reichsmark to manufacture, roughly 25 cents in equivalent value. This represented perhaps the ultimate irony of the technological gap. German fuses were cheaper, simpler, more reliable mechanically, and completely inadequate for modern warfare. American fuses were expensive, complex, revolutionary, and decisive. The secrecy surrounding production was so complete that workers at different factories didn't know other facilities were building identical components. Suppliers manufactured parts without understanding their purpose. Components were shipped between facilities in unmarked crates. The security classification remained in force until September 1945, when the war ended, and the proximity fuse was finally revealed to the public. For German prisoners of war who had witnessed the defense against Von flying bombs while held in Britain, the revelation of what they had faced was profound. They could see anti-aircraft guns firing and V-1s exploding in mid-air with mechanical precision. They understood that the same technology devastating their forces in the Ardennes was now protecting British cities with 90% effectiveness. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production firsthand. It was a realization that they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding with remarkable consistency. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war. Not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match even at the peak of its power. If America could build miniature radios that fit inside artillery shells and functioned after being subjected to forces that would destroy normal electronics, what else could they build? What other impossible problems had they solved? The officer's conclusion was that Germany had been fighting a war of the 20th century, with outdated assumptions about what was industrially possible. The proximity fuse demonstrated multiple technological advances that rippled through post-war industry. Miniaturized vacuum tubes required breakthroughs in materials science, particularly in glass composition and annealing techniques that prevented shattering under stress. The printed circuit boards used in later fuse versions were among the first mass-produced examples of technology that would revolutionize electronics. The reserve battery design using centrifugal activation was genuinely innovative. The radio circuitry was elegant and efficient, operating at frequencies that required precision crystal oscillators. But perhaps the most significant advance was in manufacturing and quality control systems. Producing millions of complex electronic devices with consistent quality required processes and procedures that barely existed before the war. American industry developed statistical quality control methods that would become foundations of modern manufacturing. Automated testing procedures verified every fuse before shipment. Supply chain management systems coordinated thousands of suppliers, delivering components to dozens of assembly facilities. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes, working to tolerances previously achieved only by master craftsmen. James Van Allen, the physicist who helped develop ruggedized vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite launched in 1958 and credited with discovering the Van Allen radiation belts used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The technology transfer went far beyond space exploration. Engineers who had worked on proximity fuses went on to careers throughout the electronics industry, bringing expertise in miniaturization, quality control, and mass production that shaped the development of commercial electronics, computers, and eventually semiconductors. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions against North Korean and Chinese forces with devastating effectiveness. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix missile, the Standard Missile family, and the Patriot surface-to-air missile all employ proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys, operate in intense jamming environments, and coordinate with other missiles. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The manual process German artillery crews endured throughout the war highlights the human cost of technological disparity. Every German artilleryman who calculated fuse settings, rotated the graduated rings, loaded the shells, and watched them explode ineffectively, or not at all, understood at some level that they were fighting with obsolete methods against an enemy that had automated the entire process. The frustration must have been profound. Trained artillerymen, skilled in their craft, executing procedures correctly, achieving textbook accuracy in their calculations, and still failing because their technology was fundamentally inadequate. Meanwhile, American gun crews with less training and experience were achieving superior results simply by loading shells and firing. The proximity fuse eliminated skill differentials. A mediocre American artillery battery outperformed an excellent German battery because American shells did the thinking. This represented a philosophical shift in warfare. For thousands of years, military effectiveness depended primarily on training, discipline, and skill. Better trained soldiers won battles. The proximity fuse demonstrated that superior technology could overcome training advantages. An American artilleryman with 6 months of training could achieve effects that a German artilleryman with 6 years of experience could not match, regardless of skill, because the Americans' shells were smarter than the Germans' calculations. German tactical responses to proximity-fused artillery revealed the desperation of facing a weapon without effective countermeasures. Field orders from January 1945 captured the evolution of German defensive doctrine. Initial directives from early December, before proximity fuses were employed on land, emphasized traditional positions. Foxholes, 4 feet deep with overhead cover, trenches connecting positions, concentration of forces for counterattacks. By late December, after experiencing proximity fuses, the orders changed dramatically. All positions must have overhead cover of logs minimum 12 inches diameter covered with 2 feet of earth. Personnel will remain under cover during American artillery fire regardless of tactical situation. Units will disperse to maximum extent consistent with command and control, no more than 3 men in any single position. These measures were theoretically sound but practically impossible under combat conditions. Constructing such fortifications required time, materials, and engineering equipment that German units didn't have. Even when built, such positions restricted mobility and prevented the aggressive tactics German doctrine emphasized. The January orders became more desperate. Units will avoid all identifiable terrain features. Movement during daylight hours prohibited in areas under American observation. Artillery positions will relocate after every fire mission. These restrictions essentially paralyzed German tactical flexibility. Avoiding terrain features meant avoiding the high ground, road junctions, and natural defensive positions that sound tactics required. Prohibiting daylight movement meant operating only at night when coordination was difficult and counterattacks nearly impossible. Relocating artillery after every mission was physically exhausting and reduced effectiveness to near zero. The final directive, issued in early February 1945, simply stated, "Units will maintain maximum dispersion at all times. Forward positions will be occupied by minimum essential personnel. Main defensive positions will be located beyond range of American field artillery when possible." This last instruction essentially conceded that German forces could not effectively defend against proximity-fused artillery and should simply try to stay out of range, an admission of tactical bankruptcy. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany proper, proximity-fused ammunition had become standard for all American artillery operations. Factories were producing fuses faster than they could be shipped to Europe. Ammunition dumps bulged with millions of shells, each containing electronics more sophisticated than entire German radar installations. German forces faced an enemy that could place automatic air burst fire on any position within range, day or night, in any weather, without requiring visual observation. The Germans never developed effective countermeasures because countermeasures were essentially impossible. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency, signal characteristics, and triggering mechanisms. Without intact working fuses to analyze comprehensively, German engineers couldn't determine the specifications needed for effective jamming. Even if they had successfully developed jamming equipment, deploying jammers across every potential target area would have been impossible given German industrial capacity in 1945. Physical countermeasures were equally futile. The fuses operated by detecting reflected radio waves from the ground or any large metal object. Reducing the radar cross-section of troops and equipment was impossible. The human body itself reflected enough energy to trigger the fuse at close range. Vehicles, buildings, and terrain features all provided strong returns. The only defense was maximum dispersion, which reduced combat effectiveness even as it reduced casualties per shell. German tactical doctrine had evolved around concentrated formations for offensive punch and coordinated defense. Dispersing to counter proximity fuses weakened overall capability, while still leaving dispersed units vulnerable to individual shells. It was a tactical dilemma with no good solution. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. They dispersed so widely that coordinated operations became nearly impossible. Morale plummeted as soldiers realized they had no effective defense. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender, specifically proximity-fused artillery. Not the fear of death, which soldiers accepted as part of combat, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. Traditional military courage was about facing danger while taking appropriate action to survive and fight effectively. Proximity fuses eliminated appropriate action. There was nothing to do, no tactical response that improved odds, just waiting in positions that offered no real protection, hoping the next barrage would land somewhere else. This helplessness broke units more effectively than casualties alone could have. It was psychological warfare accomplished not through propaganda, but through demonstrated futility of resistance. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war in Europe by an estimated 3 to 6 months. While exact figures are impossible to calculate, estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns, increasing effectiveness of defensive operations, and breaking German will to resist in fortified positions. In the Pacific Theatre, proximity fuses were credited with preventing ship losses that would have significantly delayed operations and potentially made the invasion of Japan far more costly. Against kamikaze attacks at Okinawa, ships using proximity fuses achieved kill rates exceeding 90%. Without proximity fuses, Kamikaze effectiveness would likely have inflicted unsustainable losses on invasion fleets, potentially altering strategic calculations about amphibious operations against the Japanese home islands. The strategic impact was multiplied by production scale. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated with proximity-fused fire. Defensive fire plans could cover vast areas with overlapping patterns of automatic airbursts. The psychological effect of this abundance was as significant as the physical effect. German soldiers understood they faced not just a superior weapon, but unlimited quantities of that weapon. Artillery could fire proximity-fused shells all day, every day, without concern for ammunition supply. This abundance demonstrated industrial superiority more clearly than any propaganda could. The technological legacy of the proximity fuse extended far beyond military applications into the foundations of modern electronics manufacturing. The miniaturization techniques influenced the entire consumer electronics industry that emerged after the war. The quality control methods became standard practice in manufacturing everything from television sets to computers. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training, supervision, and well-designed processes. These lessons shaped post-war American industry and contributed to American dominance in electronics through the 1950s, 60s, and 70s. The space program drew directly on proximity fuse technology and personnel. The transistor revolution benefited from manufacturing techniques developed for fuse production. The computer industry used quality control and testing methodologies pioneered in fuse factories. The intellectual capital developed during the proximity fuse program helped establish American leadership in technology throughout the second half of the 20th century. The scientists and engineers who worked on the fuse went on to distinguished careers that shaped modern science and technology. James Van Allen became one of the founding figures of space science. Merle Tuve continued leading scientific research at the Carnegie Institution. Dozens of others joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering that influenced generations of subsequent work. The industrial infrastructure created for fuse production found new uses after the war. Factories that had manufactured vacuum tubes converted to producing television tubes and consumer electronics components. Workers trained in precision assembly became the workforce for the emerging electronics industry. Supply chains established for fuse components supported the growth of consumer electronics markets in the 1950s and 60s. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technological development. Germany invested heavily in advanced weapons like jet aircraft, ballistic missiles, and sophisticated submarines. These were impressive achievements that demonstrated German scientific and engineering capabilities. They came too late and in too few numbers to affect the war's outcome because German industry couldn't support mass production while simultaneously producing basic war materials. America invested in technologies that could be mass-produced immediately using existing industrial infrastructure. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability over theoretical performance. The result was a weapon available in overwhelming numbers when needed, produced by an industrial system that could simultaneously manufacture ships, aircraft, tanks, and millions of tons of basic supplies. This reflected a fundamental difference in strategic thinking about technology and warfare. Germany sought war-winning superweapons that would offset Allied numerical superiority through qualitative advantage. The V-2 rocket, the Me-262 jet fighter, the Type 21 submarine, all represented attempts to achieve technological breakthroughs that would change the strategic balance. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers and employed effectively across multiple combat domains. That approach proved decisive. The proximity fuse combined advanced technology with practical engineering, required massive investment but produced proportionate results, was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable enough for mass deployment. In the final accounting, the proximity fuse represented everything that made American industrial power dominant in World War II. It demonstrated that free societies could mobilize scientific and industrial resources as effectively as totalitarian states, perhaps more effectively because democratic systems encouraged innovation and rewarded merit rather than political loyalty. The German soldiers who faced proximity-fused fire while still manually setting time fuses on their own shells understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national organization. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter, using methods their own military had abandoned as impossible. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The weapon that German scientists had declared impossible to build became the weapon that changed artillery warfare fundamentally. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by the tens of millions, while their enemies were still manually setting fuses one shell at a time. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial capacity and unwavering commitment to practical solutions over theoretical perfection. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through disciplined application of resources, systematic problem-solving, and industrial organization that prioritizes production over pride. The technological gap between American proximity fuses and German time fuses measured more than just sophistication of electronics. It measured the gap between two industrial philosophies, two approaches to warfare, two visions of how nations mobilize for total war. On one side, manual calculation, individual skill, and mechanical simplicity, constrained by limited resources. On the other, automated precision, mass production, and electronic complexity enabled by seemingly unlimited industrial capacity. When those two approaches collided in the frozen forests of Belgium in December 1944, the outcome was never in doubt. German artillerymen setting fuses by hand couldn't compete with American shells that set themselves automatically. German infantry in foxholes couldn't survive American airbursts that detonated with mechanical precision at optimal height every time. German industry couldn't produce countermeasures fast enough to matter against an enemy manufacturing 70,000 sophisticated electronic fuses daily. The proximity fuse didn't win World War II by itself. No single weapon ever does. But it shortened the war, saved Allied lives, and demonstrated with mathematical precision that Germany was fighting an enemy whose industrial and technological capabilities exceeded anything they could match. Every proximity-fused shell that exploded automatically above German positions, while German crews manually set their own fuses, was a small demonstration of that overwhelming advantage. After millions of such demonstrations, the message was clear. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.